Assume that everybody has some understanding of what Riemann-Roch for curves is about. I'm going to race through a scheme of how to prove it. So I have C, a curve means projective curve. It's got a function field C. So as I said, almost the definition of non-singular curve is that each OC of P is a discrete valuation ring. Yes? And so I take D is some NI-PI, the divisor, and I'm writing L of D for the same thing as H naught of OC of D. This is F in C of C. So rational functions or global meromorphic functions such that the divisor of F plus D is greater than or equal to 0. So this means that where D is positive, I allow F to have poles. And where D is negative, I insist on F having zeros. Yes? And so the formula is the dimension of this guy is 1 minus G plus the degree of D, and then possibly plus H naught plus L of KC minus D. So a kind of complementary or a dual piece. And this holds for all D. Yes? So the place where I'm going to rush is, this follows from ordinary methods of arguments and 3 key propositions. And the first key proposition, 1, is that the degree of the divisor of F is equal to 0 for all F. Yes, so 2 is the statement that there exists some sequence Dn with, these are divisors with degree of Dn tending to infinity, so increasing degree. They could be anything they like, and degree D n plus 1 minus L of Dn, always bounded. Right? So the genus of the curve is defined to be the smallest bound. Right? So this is, like in analysis, if this is bounded, then I can define G to be the maximum. And that means that the L of D is greater than or equal to 1 minus G plus this degree. Yes. 3, and this is the really key point, the really difficult point that's sort of not at all obvious. There exists a divisor Kc such that L such that degree of Kc is 2G minus 2, and L of Kc is D. Right. So this is the case. When this happens, it means that L of Kc, which is this G thing, if we compare it with 1 minus G plus the degree of Kc, right, this guy here is G minus 1, this is strictly greater. Yes? And, you know, the rest of the argument is all very, very simple if you have this. So, so here, this means that, so 2 implies there exists, so 1 implies that L of D is less than or equal to 1 plus the degree of D. Yes? So if the degree of D is negative, then if I take divisor of F plus D, then it means that this thing here would be an effective divisor of degree, the degree of F, which is 0, plus something negative, right? And so then if I add 1 point, or if I add some number of points, then I'm allowing D to have poles of order those degrees, but if I were to subtract them back off again, then I get to... anyway, 2 implies that L of D is greater than or equal to 1 minus G plus degree D, and there exists some cases of equality. Yes? And so, you know, that's just the definition of minimum. It's just this is the minimum bound or the maximum of this degree. Right? So saying it's the maximum means sometimes it's achieved. Yes? And so you work at this for a little bit and find that there exists a D primed of degree G minus 1 with L of D primed equals 0, which should not surprise anybody. I mean, you've seen all these statements. The point is, I'm just saying this is a logical structure, right? And then you work for a little bit more, and you find that for every D with degree D greater than or equal to 2G minus 1, equality holds. L of D is equal to 1 minus G plus degree D. And these are just little induction arguments. This is really very trivial. So if I look at D, for any D, I can subtract off some points. I can put this in a sequence. D is D minus 1. I can put it in a sequence where here I have degree less than 0, and here I have degree greater than or equal to 2G minus 1. Right? And so when I'm passing from here to here, I can arrange this to be minus 1, and I can arrange this to be equal to 2G minus 1. So here, we know we have no sections. Here, we know we have exactly G sections. Right? So when I'm going up here, I've got 2G steps. I've got 2G steps, and the thing has grown by G. So there must be G times where I win, and G times where I lose. Yes? And then you can do exactly the same thing with Kc minus D, right? So that goes from degree minus 1 down to degree greater than equal to G minus 1. Yes? So if you know, just know that this divisor exists without knowing anything at all about where it comes from, you get this conclusion. Right? This sequence here has to jump exactly g times, and this sequence going the other way also has to jump g times, and where they jump together, right? So if you've got, if I've got d, I can do d up to d plus p, and kc minus d greater than kc minus d minus p. And so I write down Riemann-Roch space of d and Riemann-Roch space of d plus p. I'm asking, does this increase or does it not increase? And the answer is, this increases if and only if this one stays still. Right? Because if otherwise you could take products of these and contradict this. So L of kc is g, and L of kc plus a point is also equal to g. Right? So when I go up from kc up to kc plus p, I don't allow a new pole. A new pole can't happen. And so, you know, I mean, if you know, if you relate this to Cauchy's integral theorem, this is saying I take a one form, I allow him a pole layout, a point. If I integrate around that pole, I'll find the residue. On the other hand, if I integrate around the whole of the rest of the Riemann surface, I must get 0. And so that implies that this one here has no section. So the kc is actually the same thing as omega 1 of c. Yes? And so what we have to prove is 1, 2, and 3. You know, I mean, if I was giving this as a lecture to undergraduates, I would take maybe 3 lectures to cover this material. But it is completely formal once you know statements 1, 2, and 3. If anybody wants to hear the details, please come and bother me afterwards. It's right. But I want to explain how you prove these things. And so I go to my rings of C. Right, so I told you I've got this K, I've got this field, K of C, function field. So if I take F in C of C, F not constant, then C. So I'm going to. I want to think of CF is a function, is a morphism from C to P1. Right. So in the pictures, you can still see the picture there. Here's my curve C, and here is P1. And on P1, I want to mark 0 and infinity. Right? So the places on C where F mapped to 0, those are the zeros of F, and the places where F maps to infinity are the poles of F. Right? And I want to write x naught for a coordinate on P1. So P1 is A1 x naught, and then union points x naught equals infinity. Okay, and so if I write k of x naught contained in C of C, right, this is a finite field extension. So it's you know what you study in Galois theory, and also what you study in algebraic number theory. So if I have a subring here, I can take the integral closure. Right. So when you do number theory, you start off with an algebraic number, you start off with the ring of integers contained inside the ring of rational numbers. You have a finite extension of that you call a number field, and then the number field has a ring of integers, which is the integral closure. Yes, it's a set of things that form a... So what I want to do now is take any point P in P1, right? Or let me take it in, so P not equal to infinity, just for the moment. I take any point P in P1, then I have phi to the minus 1 of P, and so this is Q1 up to Q some K, it doesn't really matter. And, you know, possibly those points are... So let's say that this is x naught equals A. X naught equals A. I've got a particular point on this line, yes? And then if I take the function f minus A, these are the zeros of the function. There may be zeros with some multiplicity. Yes? So I write O P1 of this point P. So this is a discrete valuation ring. You can think of it just as the localization of the polynomial ring in X naught at the point X equals A. Right? So I take its integral closure. In the field C of C. Yes, so this is O of C and QI, the intersection. Right? As far as the curve C is concerned, what I'm asking here is the rational functions on C that are regular at each of these points. Yes, and so you know, proving equality of these two things, each of these things is discrete valuation. If something has positive valuation here, then it will be, then it is integral over this. Yes, so this is a semi-local ring. So here's the curve is meeting this at these different points QI. I'm asking at each of these QI it's regular. Then it follows that it's integral over the base. Yes, this is just a resulting commutative algebra. And then as a resulting commutative algebra, OCQI is a free OP1 of P1 of P modulo. Yes, I'm just saying modules over a discrete valuation ring. These are finitely generated modules because they're integral, because it's an integral closure. So it's finite, and it's and so it's a free OP1 of P module, just by the theory of modules over a discrete valuation ring, which is you know, just Gaussian elimination. So this is a very, very elementary result, but the consequence of that is that the degree of f of the divisor of f minus a is equal to the degree of the field extension C x naught, C of C. Yes. So if I was doing geometry, I'd have to, if I want to draw a topological picture of this, as Riemann did, I'd have to sort of start worrying about this thing and say that the number of zeros counted with multiplicity is the same as the number of points of intersection with a neighboring fiber. So here we have the generic fiber, which is this. So that's just, you know, algebraic geometric speech for the very general fibre. This is the generic fibre of this ring extension, right? And then when I divide by the maximal ideal at this point P, I'm taking the maximal ideal here and I'm multiplying him by OC, and I'm getting these degrees of intersection at each point. Yes? And so this is constant in the family, in the fibre space. Yes? So the number of points in it, and this proves 1. Yeah? So I want to prove 2 and 3 both at the same time. I want to find a family of divisors on the curve C that grow at a completely predictable rate. Yes? And so this L of dn, you don't expect it to be equal to the degree of dn plus 1. You know, I give an argument for that, but it's makes it probably too long. Yes? So for 2 and 3, I need another ring. Yes? So we know that C is some projective curve. C is some projective curve, so it has a homogeneous coordinate ring. So this is, you know, C of x, y naught up to y n divided by the ideal of C. Okay, so this is not the ring I want. The ring I want is R of C, and so when I make this extension, I'm going to write divisor of f equals d0 minus d infinity. Yes, so the I take all the zeros of f and I group them into this 0, and I take all the infinities of all the poles of f and group them there. So that's the thing I've drawn here. Right? So I'm going to write down here R of C, O of D naught. Yes, and this is this is direct sum H naught C, O, C of N D naught, N greater than or equal to 0. Yes. So the point is that even if this map F is just the projection of C onto the two first coordinates, for example, y0, y1, x0, x1. This ring is a bigger ring than this one. Yes, it might happen. I take a curve C in projective space. Right. It might happen that it's not projectively normal. Yes. So the standard example is that I take P1 and I embed it into P3 by forms of degree 4, but missing 1. Right. So I write down, for example, P1, the original P1 is P1 of U and V, right? And I write down U to the 4th, U cubed, V, U, V cubed, V to the 4th. Yes? And you notice I didn't write down U squared, V squared there. Yes? So this is a famous example due to Macaulay, or a famous counterexample. This is a counterexample to almost everything. Yes? So the fact that the u squared v squared is missing means that this ring here is strictly smaller than this ring. Yes? And you can, you know, this is a curve of degree 4. It's isomorphic to P1. So the problem is not the curve, the problem is the embedding of the curve. I've embedded it, and I've not given it all of its homogeneous forms. Right? So, you know, it could be linearly normal. This is something that the ancient Italians called not linearly normal. So this curve is, of course, a projection of a curve in P4, yes, where I do put u squared v squared in, right? So in what way is it bad? So I told you, its homogeneous coordinate ring is not integrally closed, but also its homogeneous coordinate ring is not Cohen-Macaulay, right? So Macaulay was this famous school teacher in around 1900 in England, who wrote this famous book called Cambridge University Tract. Right? He discovered almost everything we know about polynomial rings, including, you know, some of the duality theorems I'm going to talk about immediately. Yes? So this is not Cohen-Macaulay. So if anybody wants a little exercise, it's to check that, or come and ask me how to check it. Right? So the point is that this is a free module over a free graded module over the homogeneous coordinate ring of P1. Yes? Yes? So it's a free graded module exactly because he's Cohen-Macaulay. Right, he's Cohen-Macaulay, and x0, x1 are a regular sequence. So if I cut once, I get essentially this picture like this, and then I cut a second time, and I get to a finite ring. And so, you know, this is flat over this. So I haven't left any time to explain this, but so this implies, it's equivalent to the statement that if I do pi lower star of OC is direct sum of I equals 0 up to L of O of minus AI, with AI. A0 equals 1 and AI greater than 0, greater than 1. Yes? So it's my eventual ambition to express this in a way that I can lecture it to undergraduate audience. Right. Those of you who've done, who know all of Hartshorne Chapter 2, for example, I'm writing this pi lower star of OC, so this is a vector bundle on P1. The vector bundle corresponding to so with the local modules given like this, right? And this is the direct sum of line bundles. Yes, and so what is pi lower star of omega c? So this is any proof of Riemann-Roch involves producing the canonical class. So there are lots of different ways of doing it, but they can all be described as particular cases of Grothendieck duality. So this means this thing here is Hom as modules over P1 of pi lower star OC into omega of P1, which is O P1 of minus 2. Yes? So I have to tell you where I get my dn from to prove 2, and where I get the kx to prove 3. Right? So, so dn is just n times d naught. Yes, so given the result over there, the degree of d naught is this, did I give it a name? So, it's the degree of this field extension. I'm going to call this d. So it's just this thing that you have in Galois theory called the degree of a field extension. Yes. On the other hand, L of D naught is direct sum H naught P1 O of D minus these AIs. Yes. And so, you know, I should have written this sum I equals 0 to D minus 1, right? This thing here is a vector bundle on P1 of rank D. Yes? So all of these DIs are negative, and so what's this, this dimension here? This dimension is sum of D plus 1 minus AI. Right? And the dimension of this is 1 minus G plus ND, where the G is sum of the AI minus 1, except that it's sum from I greater than 0. Yes? So one of these AIs is actually equal to 0, and I only get one section there, not, yes? So this is a very, very trivial fact. I say I'm working with this ring here, which after I've, massaged it, is a free module over the polynomial ring. It's a free graded module, and it's got generators 1 in degree 1 and all the others in degree negative. Yes? And so Kc is the divisor corresponding to line bundle, this pi lower star omega c, made into a OC module. Yeah. So I'm sorry. To be honest, I haven't prepared this completely properly. But this thing here is an OC module. And this is an absolutely fundamental part of Grothendieck duality. Namely, I'm taking something here which is, I'm making the dual of this module, right, over a smaller ring. And I'm making it into a module over the bigger ring by pre-multiplication. So if I want to know how an element in here acts on this, it acts by pre-multiplication. So having once made this into a module over pi lower star OC, the C is basically the relative spec of this ring. So look, I'm sorry, this is a very easy argument, but it's quite a subtle argument. And I have to stop it now, because otherwise, if I say any more, it will be even less convincing. Okay, so I'll answer questions on this if any of the students can sum up courage. I mean, there's quite a lot of things to say about this proof. And, I've made different attempts to write it down correctly, which haven't yet completely materialized into a chapter that I can put on the web. Okay, so let me pass on to another topic. Let me just pass on to another topic. So if this is confusing you, if you don't like what I said, then please forget about it. So remember my general policy, my general subject is I want to go from X plus data, usually a divisor, goes to a graded ring. And then I want to go from a graded ring R back to X by making product of R. Yes, and the product of R comes with sheaves O, so this is X, and it has also these sheaves OX of N for all. Yes. So I'll explain exactly what this construction is in more detail tomorrow. And I want to give more examples of applications of these ideas. And so if I write PG equals, I want to look at surfaces of general type. So I've got X, some X, which is a surface. So earlier, when I started the lectures, I said Riemann surface of genus G, and so everybody knows what that is. So a surface of general type, let me just assume that general type means Kx ample. Right, or Kx nef and big, if you want, but it doesn't, you know, everything I'm going to say here is just as easy or just as problematic as when Kx is ample as nef and big. This just involves more messing around with known singularity theory. Yes, I want to write PG is H naught of Kx. And I want to assume that Q is 0, so regular. So Q is dimension H1OX. And, you know, the kind of thing to think is most of the surfaces that I can handle have Q equals 0. This H1OX is some kind of cohomology group whose definition you've read and in some cases understood extremely well, in some cases not understood. And telling you that it's 0 just makes life a lot easier. Right, so chi of OX is 1 plus PG. Right, and I want to look at Riemann-Roch for n times Kx. Right, so this is my usual thing here, x plus some data. The data is kx, which I'm assuming is ample. Yes? And so Riemann-Roch for kx says that the dimension of h0 of x n kx is equal to 1 if n is 0, pg if n is 1, that's just the definition of pg, right? And it is chi of ox, so 1 plus pg, plus k squared times n choose 2, if n is greater than or equal to 2. Yes? So this value here is exceptional. It should be, it's not 1 pg all the way. It's 1 pg all the way after n equals 2, and n equals 1, there's only a pg in it. Right? So this is really a formula for chi of ox of nkx. And then I'd have this formula for all values, but this would include h2, which is 1 in this case. Yes? So I'm going to play with this formula next time. I'm going to show you a little trick that makes playing with it very, very quick and easy. But today I want to apply it as it is. Right, so I want to look at pg equals 4, k squared equals 5, and pg equals 4, k squared equals 6. And so, you know, you can also ask k squared equals 7, and so on. And it will eventually get completely intractable. But anyway, these already give us plenty of things to think about. So let me look at pg equals 4, k squared equals 6, 5. First, so this means I look at h0 of kx, I see 4, so I write down x1 up to x4. I write down the basis of it, right? And then I ask, who is h0 of 2kx? Yes, so I look at the formula. It says I'm supposed to do 1 plus pg, which is 5, and then n choose 2 is 1 times 5, so this is 10. Right, and here, if I write down S2 of xi, yes, I hope everybody knows the formula. Pn and forms of degree k is n plus k choose k. Well, that's also n plus k choose n. Yes, so I hope everybody's familiar with this. I mean, I wrote down Newton explicitly Newton polygon for plane conics, of which there are 6, and that number 6 is 4 choose 2. Yes, and so there are 10 of these. Right, and so let's hope they form a basis. And then if you ask for 3k, we're going to find, I think I've done this calculation somewhere in my notes. So this number here was 5 choose 2 is 10, and then the next one up is 6 choose 2, which is 15. I'm sorry. Right, 6 times 5 times 4 divided by 6. Yes? And so there are S3 of xi is the same number, 20. Right? So this number is 20 because it's 5 5 plus 3 times 5, yes? And what happens when I go to n equals 4? Then the same coincidence appears, yes? S4 of xi. The number of monomials is 7 times 6 times 5 divided by 6 is 35, and this number is also 35. Yes? Maybe this goes on forever, right? So think about S5 of xi. So, you know, this is 8 times 7 times 6 divided by 6. This is 56. Right? And this number is 55. Yes? And so this says that if I look at phi k from x into P3, this is the map, P maps to x1 of P up to x4 of P. Yes? This could be an isomorphism of x with x5 hypersurface of degree 5 in P3. And that hypersurface, you know, if you ask what is the homogeneous coordinate ring of this x5, then he is polynomial ring x1 up to x4 divided by all the forms that vanish on this x5, divided by f5. This is a principal ideal generated by this f5. So it's a little exercise to see that this will now work forever. Yes. So what happens? Any other cases? So this is the subject of my conference talk on the Friday. There isn't another possible case, namely, it could happen here that there is a quadratic equation holding between the xi's. Right? If that happens, then this map cannot be a morphism because the degree of the image would have to be divisible by 5, and it can't be a plane and it can't be a quintic. Yes? And so the only way that this calculation can fail is if this map has a base point, if kx has a base point. Right, so I'll explain this on the Friday lecture. I want to do something else now, right? But it can happen, this blows up one point, and then it's a 2-to-1 map from x to a quadratic. You know, a bit like hyperelliptic, except that I have to, you know, allow this blow up to happen before I do the double cover. Yes. So this is studied by, of course, Enriquez and Kadara and especially Horikawa. So this was Horikawa's first very important paper. And it's this thing I'm talking about on Friday, Friday at the conference. Yes? And so, you know, I mean, I want to do this also by graded rings, and the graded ring is sort of one of these things that goes to Gorenstein codimension 4, and that is, you know, one of the frontiers of knowledge. I mean, I can do it, so it's solved, but nevertheless, there are lots of other problems in the close neighborhood of this one. Right, so let's do PG equals 4k squared equals 6. Right, and this illustrates a different point. So now, you know, in h0 of kx, I still get 4, x1 to x4. When I do h0 of 2kx, right, the same formula here, exactly the same formula, gives me 11. right? And so I've got S2 of xi, 10 vectors in a given 11-dimensional vector space. So if they're, assuming they're linearly independent, which I'm going to do, then I get a y there. Yes? So, you know, if you want to understand the canonical ring of this surface, you'd better work with graded rings with generators in degree 1 and in degree 2. So this isn't a matter of some kind of aberration or some kind of hyperelliptic degeneration or some kind of deliberately not working with straight projective space. If you want to be able to capture these surfaces completely, you better do graded rings with this arrangement, right? So H naught of 3kx, this is also very interesting. So what am I getting? I'm getting the usual 5, and then it's 3 times 6, right? So I'm getting 3 times more than I got in that calculation, right? So this is chi of OX plus 3 times 6, 18. This is 23. Yes, and what monomials do I already know here? Well, I've got S3 of xi, so that's the same number as there, and I've got xi times y, yes, and that's 4. And so therefore, there exists a relation. This is just a linear dependence relation in this vector space, and I can assume it's x1 times y equals a3 of x1 over x4. Yes? So, you know, when I have this graded ring, that's telling me how to embed x into weighted projective space, and it's also telling me how to write down the equations of x. Yes? So if we just talk about embedding and we don't know the equations, is not very much information. Whereas here we're deriving the complete set of equations. X naught 4kx, what happens here? Well, this is 5, and then it's 6 times 6. Right, so this is 41. Right, so what am I getting here? I'm getting S4 of xi, so that's the same as before, that's 35. And I'm getting quadratics in the xi times y. Yes? However, I already have a relation here. So if I write down quadratics in the xi times y, this is, of course, 10. Yes? But minus 4 times this relation. So I call this one S. Right? So if I take this relation and multiply them by any of the xi's, I get a relation between these monomials. Right? So this leaves 6. This is 41. Right? So if we're very lucky that these 41 monomials will exactly base this vector space, but I've got another guy here. I've got y squared. Right? And so I must have an equation saying, well, assuming these guys are linearly independent, I must have another equation saying that this is B4. Right, or of course it could, anyway, I'm completing the square here. I'm possibly changing the y retrospectively, completing the square. Yes, so that says, well, I want to find at least some examples of x, so I'm going to take complete intersection of degree 3, 4, contained in weight projective space 1 to the 4th, 2. Yeah, so this is just proj of this space. Right? So, you know, you can also describe this as the projective cone over the Veronese embedding of P3. Right? If I write down all the quadratics in the xi, that's coordinates on projective coordinates on the second Veronese embedding of P3. P3 embedded by its O of 2. Right? If I add one more variable, I'm just putting that in a projective space of dimension 1 more and taking the cone. Yes? And so I'm going to write down 2 equations here. One of the equations says we don't pass through the origin. Yes? And so, you know, actually we're in a nice non-singular space here. So we're not involved, you know, the ambient space has a singularity, but the embedded variety x doesn't pass through that singularity. And so we're just, you can think of this as a nice ordinary construction of a projective variety. Yes? Now, there's one kind of last point, one last advantage of this method, which is that let's now look again at phi kx from x to P3. So assume that all of these guys are as linearly independent as they can be. Do we know what the image is? Do we know what the image is? So in other words, take these equations, that's the equations of this 3, 4 in this space, and eliminate y. Can we write down an equation that doesn't involve y among those variables? So of course we can. Namely, y, as a rational function, we already know y. Y is this A3 divided by x1. Yes? And then if I plug that in here, I get the equation A3 squared equals x1 squared times B4. Yes? So take completely general cubic form, completely general quartic form, and write down this equation. What do we get? So this is a sextic hypersurface, a hypersurface of degree 6, which is very good because it's the image under this divisor of degree 6. Yes? So if it were mapping to a non-singular sextic, for example, a non-singular sextic has canonical class O of 2, so k squared is 24, which is much bigger than the case here, and PG is 10 or something, so it's just completely wrong. So we can't, it's not possible for X to map isomorphically to a surface of degree 6 in P3. Right? What is this? Can anybody detect where this is singular? So, you know, I mean, you're not supposed to be computer algebra programs. If you're at a point where x1 is 0 and a3 is 0, right, then there are no terms that are linear in the equation. Yes? And so this means, what this means is, here is the plane x1 equals 0. Yes, inside this there is a curve given by a3 equals 0, and it's a plane non-singular cubic. Yes, and the surface x bar has an ordinary double locus along it. So it looks like this. Right, it's an ordinary double locus all the way along this curve. Yes? So who is x? So I can take this picture and I can normalize. I take the normalization in the ordinary sense, in the local sense. I'm just taking apart these two different surfaces, two different local directions along the node, right? And that gives me this x. So you know, in however you want to think of the canonical sheaf, k of x bar, or omega of x bar, is O of 2. It's OP2 restricted to x bar. And by unbuttoning this surface along its double locus, I'm subtracting one copy of x1. So kx is kx1 minus x1 equals 0. Right. So you can describe this as in terms of the conductor ideal of the normalization. You can describe many different ways. Yes. So this presentation, hypersurface degree 3, 4 in 1 to the 4th 2, is really better than this one. This one is the one canonical image. What happens if you take only sections of kx? Of course, you can follow this through. You can study it in detail, and Enriquez and Horikawa did. But this thing here is just much cleaner, right? I'm asking the question how to write the graded ring corresponding to a general surface with these invariants, and I get out a reasonable answer. Yes. So there's a kind of little warning that in exactly the same way as the Horikawa quintics, this can break up, and there've been 4 or 5 papers written on what happens when x has a base point. So at the linear system kx here could blow up some points, and then it could then be a double cover of a quadric, and basically all kinds of complicated things happen. So if you go to this k² equals 7 case, Ingrid Bauer wrote a book on the case, and I currently have a Mexican graduate student who is working out the corresponding graded rings, and it is very complicated. It's really very, very difficult calculations. So in the remaining lectures, sorry, I've already gone over time. In the remaining lectures, I want to talk about some more of these surface constructions, but I really want to get into threefolds. Sorry for going over time.